Okay, hello everybody. Welcome to the practice exam solution guide. So I'm going to film this in a couple of segments probably because I don't have time to do the whole thing right now. Um, but let's see, I'll stitch it all together into one video. So before I start solving the practice exam, I want everybody to know that the practice exam is not comprehensive. Okay, so it doesn't cover everything that we learned that is could possibly be on the test. In fact, there will probably be things on the test which are not on the practice exam. This is just an example of a selection of problems which could be on an exam, and it's to give you guys an idea of like what the style of exam questions that I ask when I give these take-home exams, because they're a bit different than the ones that we do in person. Okay, so if you want to have help studying for the exam, then you should really come to my office hours or go to the SI sessions and make sure that you have a comprehensive plan that's going to make sure that you know all the material which is in the following sections. We did 8.1, 8.2, 8.3, 4, we skipped 8.5, and then we did 8.6 and 8.7, and then in chapter 1 we did sections 1 through 7. Okay, so that's what's going to be on the exam. Just a reminder, we're doing section 5 on Monday of this week, and we're doing section 6 and 7 on Tuesday of this week. Okay, so Wednesday will be a review, and then the exam will take place on Thursday. Okay, so let's get started. Okay, so question 1, we're asked to sketch the graph of a linear function y equals f of x, which has a non-negative slope and a y-intercept which lies below the x-axis. Okay, so non-negative slope. Non-negative means it should be larger than or equal to 0. And y-intercept which lies below the x-axis. Okay, so b should be less than 0. So we should have m, our slope should be larger than or equal to 0, and b should be strictly less than 0. Okay, so a function which has a non-negative slope, I'm just going to choose one that has a positive slope, and I'll choose b to be, I don't know, -1. You could choose any number of lines here, but the one I'm going to choose is m equals 1 and b equals -1. Then both of my criterion will be satisfied. So I'll put a intercept there at -1, and then I will go up at a steady rate here, and I will go down at a steady rate. Okay, so that'll be my line. And remember, slope-intercept form is going to be y equals mx plus b. So we're just going to take our m and our b from our picture, and we're going to put them in here. So mine's going to be y equals just x plus x minus 1. Okay, so that's the slope-intercept form of the line that I drew. Again, you could have drawn any number of lines, but you need to make sure that your line has a y-intercept somewhere in this highlighted red region. Okay, that's beneath the x-axis. Okay, that's where we need our y-intercept to be, and we need to be moving in any range of directions from, here to here. We need to be somewhere in this range, okay? If our slope is going down like this, then our slope is going to be negative, and we require that our slope should be non-negative, okay? So we don't want that. Okay, so last part of this problem, they ask us a linear function with a non-negative slope is going to be always, sometimes, or never an increasing function. Well, remember, the definition of an increasing function was that if x2 is larger than x1, then this implies that f of x2 should be larger than f of x1. Okay, that's what it means for a function to be increasing. And we can take a look at my function here, for example. That's going to be true, right? If x2 is larger than x1, then by the addition property, we have that x2 minus 1 is going to be larger than x1 minus 1, right? And these are going to be the y values for those two coordinates. So it's plausible, or rather, I guess it's true for my line that I drew. However, we're asked, we have this kind of pesky sometimes here, so we should check if it's possible that we could have a line which has a non-negative slope and a y-intercept which lies beneath the x, or no, we just have non-negative slope. So we should check if we can have a non-negative slope function which is not an increasing function, and we can, because we can choose m equals 0, so then that would mean that y is equal to a constant, and if you have x2 is larger than x1 and we plug in, we would get we would not have that this implies that c is bigger than c, because that's not true. Okay, so this implication can't be true because the conclusion is never true. Okay, so we have to consider the fact that we could have a horizontal line. Okay, non-negative means our line could be horizontal. This is the line y equals c. Okay, so my answer for this would be sometimes. Okay, if we interchanged this word here, non-negative, if we made that word positive, then we would get that it would always be an increasing function. But non-negative and positive are different. Okay, so that's that question. So we can move on to question 2. So question 2, we got some true and false. I often put a true and false section on these exams, and I'll do like these 2-point things where you have to say whether it's true or false, and if it's false, then briefly explain why. Okay, so we have a bunch of statements here, so let's just go through one by one. Starting with A. Okay, so we want to evaluate, is this true? Is this equality true? Okay, so we have x times y to the negative a power, and this looks a little bit like our rule. Remember, the rule that we had was if we have x to the negative a, then that is going to be equal to 1 over x to the a. We move it to the denominator and we make the power positive. Okay, but this is actually going to be false. And the reason is x times y to the negative a is actually going to be equal to x times, well, we only have the negative a power being applied to y here. Okay, if we had parentheses around here, then maybe we could have that be true. But we don't have these parentheses, so the negative a power is only on y. Okay, we have a hanging kind of 1 power here on x. So this is x to the power 1 times y to the power negative a. So we will get x to the power 1 will just stay the same, and y to the negative a will become 1 over y to the a. And so our answer would actually be x over y to the a. Okay, and these things are not the same. I should have just drawn it all the way in. Okay, these two are not the same. All right, so we need to remember that if we want to distribute a power onto things which are being multiplied, we need to see these parentheses, like right here in purple. If we had these parentheses, then it would be true. Okay, we'd just move everything to the bottom, but we would need to keep our parentheses like this still. Okay? So we only distribute powers if we have parentheses. Okay, so let's check the second one here. We've got x to the 2/3 power, and we're rewriting that. We're writing that that is equal to x squared to the 1/3 power. Well, you can check if this is true by seeing if you can go in this direction. Well, if we had x to a power, we would multiply those powers. And if I took 1/3 and I multiplied it times 2, I would get 2/3. So this looks good so far based on our understanding of the rules, which we learned in, well, one of those lectures. And now let's see this one here. Well, from here to here, the only thing that we would need to verify is that is a 1/3 power the same as doing a cube root? And the answer is yes, it is. That was one of our definitions for doing fractional powers or rational powers. Okay, so that one's true so far. So we know that we're good here and we're good here. So let's check the last one. The last one is saying, okay, can we do the cube root first and then square? Is that going to be different than squaring and then doing the cube root? And that was another one of the rules that we learned. We can do these square roots and powers in any order that we please. So this is also fine. Okay, so all three of our equal signs are going to be okay. I'm going to go ahead and call this one true. Okay. So next up we've got some rational expressions which we're supposed to add. Okay, rational expressions, and we're adding them. And it looks like the statement is saying what we should do if we want to add these rational expressions is just take the top and just add it up, collect like terms on the top, and then just collect like terms on the bottom. Okay, just take, we get this denominator here by just taking, you know, x minus 1, and we add x and we subtract 2, and we would get 2x minus 3. And that's simply just not how we add rational expressions. It's not how we add fractions whatsoever, actually. We have to, anytime we want to add fractions, whether they're rational expressions like this or just regular old fractions, if we want to add them, we have to first find a common denominator. So this is false. This is a really common mistake that students make when they're first learning how to add rational expressions. We can't just add the denominators. If we wanted to solve it correctly, we would need to find a common denominator. But the question doesn't ask us to actually solve it. It just says, if the statement's false, briefly explain why. I think, you know, if you left it at, we can't add denominators like this, I think that would be fine. I'd give you full points for that. If you wanted to, you could go ahead and add them correctly, but I don't think it's necessary, given the directions. Okay, so part D, another equality here. We're supposed to decide whether or not, if we have A plus B plus C, three things being added, is it true that we can just distribute this 2 right on to all of these terms here and just get A squared plus B squared plus C squared? And it's definitely not true. And you can figure it out pretty easily by just choosing any counterexample. We'll try, I don't know, A equals 1, B equals 2, and C equals 3. So let's try. We'd get 1 plus 2 plus 3 would be 6 squared. So the left-hand side would be 36. We'll leave a question mark above this equal sign for the time being. And now we'll do A squared, that would be 1. And we'll do B squared, that would be 4. And then we would do C squared, that would be 9. And the question is 36 going to be equal to 9 plus 4 is 13 plus 1 is 14? No, is the answer. So we can put a strike through on these equal signs because that's not going to be true. Okay, so that's one way that I can justify my answer of false. I just say, well, try it out with 1, 2, and 3. If it doesn't work for one choice of A, B, and C, it certainly doesn't work for every possible choice of A, B, and C, which is what this statement is saying. Okay, so it's false. All right. So this is kind of like a repackaging. It's a trinomial repackaging of the fact that if we do a plus b squared, right, you have to FOIL, right? If we want to take this expression, a plus b plus c squared, what we would need to do is write a plus b plus c times a plus b plus c, and then we would need to distribute the a onto all three of these terms, and then we would need to distribute the b onto all three of these terms, and then we'd have to distribute the c onto all three of these terms. That's what we would have to do if we wanted to actually multiply that left-hand side out. And you could do that and collect all of the terms, and you'll see that you'll get a squared plus b squared plus c squared plus a whole bunch of other stuff. So that would be another way of showing that this is false. But you can also just provide a counterexample, because you only have to show that it's not true in one particular case. Okay, so that's that one. And the last one looks a little bit confusing. Let's see, it says we can compute the nth root of a negative number as long as n is a positive integer. Okay, so what we're saying is just n should be something like 1, 2, 3, 4, these sorts of numbers. Those are positive integers. And we're saying we can do the nth root of a negative number as long as n is gonna be a positive integer. And that's not quite true. In fact, if we just choose n equals 2, we can't do the square root of, say, -1. Well, we can, but we can't get a real valued solution. So maybe let me not say we can compute, but maybe I should have written on this problem something like, and get a real number as a solution. Something like that. So let me write, we can't do the square root of -1 without using imaginary numbers. And we aren't using imaginary numbers in this class for the time being. That might change later. Okay, so we'll move on to question 3. Oh, so this was false. So if you really wanted to say something, you could say something like, we can only take nth roots of negative numbers when n is a positive and odd integer. Okay, so 3, 5, 7, 9, odd numbers. Okay, we can do odd powered roots of negative numbers. Okay, so question number 3. Let's see here. In words, explain the difference between a quadratic equation and a quadratic expression. Okay, well, a quadratic expression has the form ax squared plus bx plus c, while a quadratic equation has the form ax squared plus bx plus c is equal to 0. Okay, so in other words, the difference between the two is that in one of them we have an equal sign and in one of them we don't. So I would say the difference being equality to 0. So an example of each would be, I don't know, we could do 2x squared minus 3. And for an equation, we could do x squared plus 7x plus 6 is equal to 0. Or you could put any number you want on the right-hand side if you want, as long as it's a quadratic equation. Okay, so now we're supposed to explain the purpose of the quadratic formula and how to apply it. Well, the quadratic formula is something that we use to find the roots of a polynomial, okay? Or not a polynomial, we use them to find the roots of a quadratic polynomial. So I would write something like, we use the quadratic formula to find the values of x such that the quadratic expression evaluates to 0. One can apply it by identifying the constants a, b, and c such that ax squared plus bx plus c is equal to 0, and then plugging in to x equals negative b plus or minus the square root of b squared. My handwriting is getting bad here, I'm writing fast. B squared minus 4ac all divided by 2a. Okay, so your answer doesn't necessarily have to be as detailed as this, but this is probably, strictly speaking, the best answer, or one of the best answers that you could give to this problem. If you wrote something like, we use it to find the zeros of quadratics, or the x-intercepts of a parabola, or something like that. And then you mentioned that you just figure out what A, B, and C are and then plug in, then you should be good to go. Okay, so now we have a problem here where we're supposed to actually solve this thing. So this would be one that we could apply the quadratic formula to if we wanted, but I don't want to deal with all of that jazz, so I'm just going to try to factor it. So I'm going to try to factor it using grouping, I think. Yeah, I'm going to use grouping. So when I put something like this on here about showing all work, I really want you to be as detailed as physically possible. So here's like the standard of work that I feel like I would hope that you guys hold yourself to on these exams. Be something like this. So first of all, I'd write something like, let's try grouping. We want two numbers which multiply to a times c, which is, in our case, negative 45. And add to b, which in our case is negative 12. Okay, so what I would do is I would split this thing up. I would write all of the different factors of 45. It could be, let's see, 5 and negative 9, negative 5 and 9, or we could do 15 and negative 3, or negative 15 and positive 3. If I want them to add up to negative 12, I think the ones I'm going to have to choose are negative 15 and 3 here. Wow, that does not look good when I highlight that. Okay, so I think I want these last ones, negative 15 and 3. So now break up the middle term. And I would get something like 5y squared minus 15y plus 3y minus 9 is equal to 0. So all I did was I just rewrote negative 12 as negative 15 plus 3. Okay, that's all I did. So I broke up the middle term, and now I'm going to take a GCF. Out of each of those things there, I'll get something like 5y times y minus 3 plus, I'll just take a 3 out of the second one. We get 3 times y minus 3 is equal to 0. And now I anti-distribute. And I get 5y plus 3 times y minus 3. Okay, where the 5y plus 3 came from, oops, it's supposed to be a highlighter, came from this 5y and this 3. So that's where this term came from. And then the y minus 3 came from these two guys here, okay? So if we were to distribute out the 5y onto y minus 3 and the 3 onto y minus 3, then we would get back to where we were just before. Okay, we call this anti-distributing. Okay. All right, I'm gonna pause for a minute, and then I'll come back and record the rest of this a little bit later. Okay, I'm back to do the rest of the practice exam. So I think I left off with this problem. So we'll move on to number 4. By the way, sorry if there's feedback on the microphone. It's raining really hard right outside my window. So hopefully you can hear me well. Okay, so the next problem, looks like I have some random gibberish there. Okay, so the next problem, we are supposed to deal with some inequalities. So here we have some inequalities with absolute value signs, and we're supposed to match each one to the answers in the answer bank. So let's just take a look at what these say. What this first one says, I here, says if we take 2x minus 3 and we take the absolute value of it, or in other words, the distance from 0, then we get that distance should be larger than or equal to 1. Okay, so in other words, 2x minus 3, if we were to draw a number line, we need 2x minus 3 to be somewhere between 1 and infinity, or somewhere between negative 1 and infinity. Okay, so things like this are always going to give us one of these OR problems, okay? So we should be thinking that it's going to be B or C. But let's go ahead and actually solve it and see what we get. Well, if we took 2x minus 3, we wanted that to be larger than or equal to 1, then what we're really saying is either 2x minus 3 should be larger than or equal to 1, or we should get that the negation of that, so negative 2x plus 3 should be less than or equal to negative 1. Okay? So we can just solve each of these individually. We'd get add 3 to both sides. We'd get x should be larger than or equal to 4 divided by 2 is 2. And then we'll have OR let's see, we would move the 3 over, we'd get -4 on the right hand side, and then we divide by -2 and flip the sign, so we would get wait, hang on, we get -4 on that side, greater than or equal to -2x, and then we would divide by 2 and we get x is, hang on a second, something's wrong here. Sorry, this should still have been a greater than sign. Mistake I made there. My apologies. I should have kept the sign the same. And we want this to be a +1. Sorry about that. So what should we have done? We should have subtracted 3 from both sides, and we would get -2 on this side, and then we would divide both sides by -2, and we would get x, and then we would flip the sign because we divided by a negative, and we would get 1. Okay, there we go. So it looks like B is going to correspond to I. Okay, now the remaining ones we can go ahead and solve, or we could also just recognize that one of them is a greater than sign and one of them is a less than or equal to sign. We know that when we have less than or equal to sign on an absolute value thing, it's going to correspond to one of these and boys. And then when we have this greater than sign, it's going to correspond to one of these ors. Okay, so I think the correct order here is going to be A and C, and that's just done by virtue of elimination, really. But you can do the same kind of process here using the tips and tricks that I gave during, I think it was the 8.6 or 8.7 lecture. I gave a key for how to interpret these absolute value signs being either greater than or equal to or less than or equal to. I had a whole guide on which ones went with and which ones went with or, and how to interpret those. So you could put those on a flashcard and study those if you wanted for something like this. Okay, 1 second. Okay. So let's keep on going with this problem. Looks like next we're supposed to graph each inequality on a number line. Okay, so the easiest thing that's going to help us do this is just by simplifying each one into a single inequality. So I'm going to divide both sides by 4, and I would get x is greater than 3/4. If I was going to draw a number line, I don't know, I usually like to put 0 just for fun. And then here's 3/4, and I would draw an open dot on 3/4, and then x should be larger than that, so I'm going to draw the arrow going to the right. Okay, open dot corresponds to the fact that I have a greater than sign, but not a greater than or equal to sign. Alright, the next one is an interval notation problem. So it looks like we have the interval that goes from -infinity to +3, and it's exclusive. Okay, by exclusive, I'm referring to the fact that we have a parentheses around this 3 and not a bracket. When we have a parentheses, that means that we don't include, okay? Parentheses go with things like strict greater than signs and open dots. Meanwhile, brackets go with things like less than or equal to signs and closed dots. Okay, so I'm just going to put 0 on here, and then I'll put 3 here, and I'm going to go with an open dot on 3 and arrow to the left, because we go all the way to -infinity. Okay, so this expression literally means, translates to, this is the collection of all numbers which are less than 3. Okay, it's like a bucket, and inside our bucket we hold every single number, which is satisfying the property that that number is less than 3. Okay. Now this next one here, we've got x is larger than 2 and not more than 7. Okay, when you see things like this keyword here, not more than, or keywords, I guess, that means less than or equal to, basically. When we say something like larger than, that means something like strict inequality, okay? So we should have that x should be larger than 2 and not more than 7. So let's interpret this into interval or inequality notation first. We should have x in the middle, and it should be bigger than, strictly bigger than 2 and less than or equal to 7. So if I was going to draw this on a number line, I'd put 0, 2, and 7. I'd put a closed dot on 7, open dot on 2, scribble in between. Okay, so be careful about this language. When we hear something like not more than 7, well, it's true. It's going to be true that 7 itself is not more than 7. That's true, right? So we include it. That's why we have a greater than or equal to sign there. Meanwhile, when we say the left-hand side, when we look at 2, it wouldn't be true to say that 2 is larger than 2. 2 is actually equal to 2. Okay, so that's why we keep this less than sign as a strict inequality. All right, so that's how I would draw that one. And this last one is like a bit of a tricky one. What does it say? It says the absolute value of x is less than or equal to 0. Which, if we were going to translate that, that means that this is going to be x is not more than, oops, that's a that. Is not more than 0 units away from 0. Which is kind of like saying, well, there's only one number that we could really put in there that's going to give us a true statement, and that's the number 0. 0 is the only number which is less than or equal to 0 in absolute value. If we were to plug in, say, -1, well, we would plug in -1 here. The absolute value would make it +1, and +1's not less than or equal to 0. So we're going to basically get no other numbers other than just we're going to have a closed dot on 0, and that's it. All right, that one's kind of tricky. Okay, let's move on. Question 5 deals with domain and range, it looks like. So, okay, we want to write a collection of inequalities or intervals to express the domain of the function f of x equals the cube root of x minus 7 divided by x squared plus 7x plus 6. Now, if we remember from our lecture on domain and range, when the domain is not explicitly written, we just assume that the domain is the collection of all numbers for which this expression, this rational expression, makes sense. Okay? And the only time that rational expressions like this are going to not make sense is dividing by 0 or even-powered root of a negative number. Now I can see in my particular expression that I have a cube root on top, okay, and that's an odd-powered root, which means it's okay for the stuff that's underneath to be negative. I can do the cube root of a negative number. So that's not really going to give me any trouble. So I think really the only thing that I need to worry about is dividing by 0. And so I need to find out when is this denominator going to be 0? And then when I write my collection of inequalities and intervals, I'm going to write it in a way that excludes any of the numbers which would make this denominator equal to 0. So I'm just going to check when is x squared plus 7x plus 6 equal to 0? Well, we can factor this expression as x plus 6 times x plus 1. Or you could use the quadratic formula if you want. And this is going to happen when x is equal to -1 or x is equal to -6. Those are the times when that expression is going to be 0. So these are the numbers that I want to exclude from my domain. So I could write my domain in one of three ways. I could write x is not equal to -1 and x is not equal to -6. So that's answer number 1, which is okay. Answer number 2, I could write -infinity is less than x is less than or equal to 6, or, oh sorry, not less than or equal to, we want to exclude that 6 there, or 6 less than x, oh shoot, that should have been a -6, -6 less than x less than -1, or -1 less than x less than infinity. Okay, so I can write 3 inequalities like that, or I could use interval notation and say something like -infinity, comma, -6 with the parentheses because I don't include it, union -6, comma, -1, union -1, comma, infinity. Okay, so any of these 3 answers would be acceptable here. Okay. Really, they're all 3 saying the same thing. They're just saying you can plug in any number that you want except for -1 and -6. Okay, so next up, we have a range question. Okay, so we're supposed to write a collection of inequalities and intervals to express the range of the function f of x equals 1 over x, and this time they give us the domain. Okay, they give us the domain here. It's going to be from -1 to 0, but not including 0, obviously, because we can't plug it in to this fraction. That would give us 1 divided by 0. We're going to get all the numbers which are less than 0 but larger than -1 or equal to it, and then we're going to get the numbers which are between 0 and 1, including 1 but not including 0. Okay, so if we remember what the function 1 over x looks like, this was one of the functions that was in our library of functions. We could draw it, and I think it's going to be instructive to see the graph for this particular problem. It looks kind of like this, and on the other side it looks like this. And our domain here we're kind of taking to be like, here's -1 maybe, and here is +1. And our domain we are going to take to be all of the points which are between 1 and -1, but we're going to exclude 0. So here's our domain. If we remember, the way we defined the range was we defined the range to be the set of values for which, along the y-axis, for which, if we drew a horizontal line, we would hit the graph at some point which is in the domain. Okay? So what we're really considering is going to be all of the y values of the points which correspond to the domain. So I'm going to draw them all here in purple. We want to look at all of these points here, going all the way up, 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 up forever. And then from here on the left side, we start here and go down, 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 down forever. And we want to look at all of those y values. Okay, so in particular, we're not going to include the sections of the graph which are out here in this blue area or out here in this blue area. Okay, and as we can see, we're only going to have those y values. We would only have a y value in that region if we took this point like way over here, and that's not in our domain. So if we consider the collection of y values for which we have an intersection with that horizontal line for some x value which is in the domain, we're just going to be talking about all of the y values which are sort of like, how can I describe this? Maybe I'll use green and red. I'll use red to describe the area that we don't hit. So this region here, along the y-axis, we're not going to hit, because if we draw a line like this, okay, everything that's underneath that line and above this line, no, that line should be lower. It should be right there, probably. Okay, everything that's between these two lines is not going to be hit, okay, because the only places on the graph of 1 over x where we have heights of the function lying in between these two lines is going to be these sections of kind of blue highlighted stuff, okay? Whereas the region of y values, which I will highlight in green along here, we can draw a horizontal line from those points and hit our graph at an x value which is in the domain, okay? Which is in the domain. So the range of this function is just going to be all of these numbers going down from this point right here, going down to negative infinity, and going from this point right here, going up to positive infinity. So the lowest point on the graph of this function is going to be negative infinity. And then we go up, 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 up until we hit, my graph is getting a little bit cluttered now, but let me highlight with purple this point right here. I want to know what is the y value of that point there. Well, I know the x value of that point is when x is equal to negative 1. So I plug in negative 1 and I would get 1 over negative 1. And I'm going to use a bracket because that is included in the domain, so we should include it in the range. And then I don't hit any of these values in this kind of red highlighted region of the y-axis. But I do hit then everything which is above this point over, man, I'm running out of colors. He's brown, I guess. This point right here is going to be my new low point, okay? I'm going to hit union, and I'm going to use another bracket, and that is the point where the x value is positive 1. So if I plugged positive 1 into the function f of x equals 1 over x, I would get 1 over 1. And then I go up to infinity. So the range for this function is going to be negative infinity, comma 1, negative 1, inclusive, union, 1 inclusive, comma infinity. Okay. So that's how we would do that problem. So I want everybody to notice here that basically what this is saying is if we take a look just at our domain here, our domain was the set of numbers which are between negative 1 and 0, and also the set of numbers which are between 0 and 1. So in other words, x, the largest that x could possibly be would be 1 or maybe negative 1. So we can see here that if we were to take negative 1 and plug it into here, we would get f of negative 1 is equal to negative 1. And we would get f of 1 is equal to 1. And we can see that all the other possible numbers which we could plug in are going to be less than that. If we take 1 divided by some number x, and the number x is less than 1, if we have x is less than 1, then this is going to imply that the number 1 over x is going to be larger than 1. Okay? And we can get numbers which are as large as we want, really, because we can divide by something really close to 0, and we could do something like 1 divided by 0.000000001, and we'd get something like, I don't know, 1 million or billion. I don't know how many zeros I've got here, right? We can get really big numbers by dividing 1 by something really, really small, okay? So that's why we get all of these numbers which are here in 1 comma infinity. And then likewise on the other side, when we take really, really small negative numbers and we divide 1 by something like negative 0.0001, we're going to get something like negative a billion or a million or whatever that number is. And so that's why we get this negative infinity here on the left-hand side. We can do all of those numbers which are really, really small, or really, really big and negative, I guess. And that goes up to the end of that interval, which happens when we look at the kind of endpoint here at when we plug in this -1 in here. Okay, so that's how we find that range. Okay. So next up we'll do question 6. Looks like we are supposed to explain in words how each function transformation affects the graph of the following parent function. Okay, so we have x cubed minus 3. We could even graph that. We know how to graph x cubed minus 3. It should look like x cubed, but it should be down 3 units. 1, 2, 3. So there's our point, and then it looks like x cubed. Okay, so we want to know how it's going to be affected when we do these various operations here. So let's try this first one. Well, we have a multiplication by 3 on the outside. I would say, since 3 is bigger than 1, and multiplied on the outside, this is going to correspond to a vertical stretch. By a factor of 3. Vertical stretch by a factor of 3. Okay. Now this next one here, I've got f of x divided by 2. But I got to be careful because I'm doing a multiplication times 1/2 on the inside, okay? Now remember, when I'm doing operations like this on the inside, things get sort of reversed from what we think they're going to be. When we add a number on the inside, that corresponds to a shift to the left, and so on and so forth, and everything feels like it's kind of backwards. So we would check, we would say since 1/2 is strictly less than 1, and we are multiplying inside, remember things inside get wonky, so when we multiply by something less than 1, we would think that would give us a compression, but actually it gives us a horizontal stretch. By a factor of 2. Okay? And I can kind of draw for a second and show you what I mean by that. Say we had x versus x squared and something like x versus x over 2 squared. Okay, I'll show you why this going from left to right is going to give us a horizontal stretch. Well, if we take x and x squared, we can try 1 goes to 1, 2 goes to 4, 3 goes to 9, 4 goes to 16. On x and x over 2 squared, we can do the same thing. 1, 2, 3, 4. What would we get? We'd get 1/2 squared would be 1/4. 2 over 2 squared would be 1. 3 over 2 squared would be like 9/4, 9/4. And then, what do we got here? 4 is going to be 4 over 2 squared would be 4. So if we were to draw these two, first one looks like a usual parabola, right? We've got point 1 comma 1 and the point, I don't know, 2 comma 4. The other one, we're going to see the point 4 comma 4 on this one, so it's going to be growing much slower. Okay, so here we get the point 4 comma 4 on here. So this is the graph of x over 2 squared. This is the graph of x squared. So we can see that what's happening here is basically we take the distance between a given point and the a given point and the y-axis, and then we basically double it in order to get the distance, the new distance for our new function. Okay, so we call that a stretch. It's as if we took the whole thing and stretched it out sideways. Okay, so we are stretching in this direction. On the left-hand side, it does the same thing. It just gets stretched wider. All right? That's just an example. Yeah, I'll leave that on here. I'll leave it down there. Okay, so we get a horizontal stretch by a factor of 2. Now here we've got one of those tricky ones again. Something's happening on the inside. I know it's going to be sort of the reverse of what I think it should be. This is going to be shift 3 units. I guess we could call it a horizontal shift. Horizontal shift 3 units to the left. Okay. We move to the left when we add something on the inside. It's a little bit counterintuitive. But just remember here, B and C are both dealing with things happening on the inside. And when we do these transformations on the inside, we're dealing with horizontal things, okay? It's either going to be a horizontal stretch or a compression if we're multiplying by some number, or it's going to be a horizontal shift left or right, depending on if we're adding or subtracting. And also, if we were to have like a negative sign on the inside, that's going to represent a horizontal reflection, right? It's going to be a reflection which is across the y-axis. Okay? Which kind of leads us into our last thing here. What we've got is negative f of negative x. Okay, so it looks like we've got 2 reflections here. The one on the inside says reflect about y. And the one on the outside says reflect about x. Okay, so that would take something which looks like this. We would flip it over to the left-hand side and it would look like this. And then we would flip it upside down and it would wind up looking like this. So the total shift is going to be basically across the origin. Okay? So I guess the way I would answer this is I would say reflect about y and reflect about x. Okay. So those are my transformations. Yeah, you can kind of see here that I guess the type of question that I'm asking here is sort of more conceptual, right? I'm not actually asking you to draw the graph of this function when we do this operation, right? I'm just asking you to explain in words how each transformation affects the graph of the parent function. Okay? So it's a conceptual question. I'm not asking you to like compute things here. Just asking you to see if you know the rules of what we should do. Okay? And I have to ask that sort of question because when you're taking it at home with open notes and no supervision, you know, I need to ask kind of these more conceptual questions. Okay, so last one, I think? Yeah, last one. The last one is dealing with compositions of functions and inverse functions. Okay, so we're given a bank of three functions. We have f of x equals 3x minus 2, g of x equals 1 over x, and h of x is equal to x squared. And the first question just asks us to find f inverse of x. Okay, so we take the function f of x equals 3x minus 2. Okay. And what we're going to do here is, in order to find this inverse, we're going to switch the role of x and y. Okay? We're going to switch the role of x and y, and then we're going to solve for y. So switch, we get x is equal to 3y minus 2. Okay, and now we have to solve for y. So I'm going to add 2 to both sides. I'll get 3y equals x plus 2. And then I would get y equals x plus 2 divided by 3. And that is going to be my inverse function, f inverse of x. Okay, so all I have to do is switch the x and y, and then solve for y, and that's how I get my new inverse function. Okay? You can always check if this is an inverse by plugging. If I take my inverse function and I plug it into my original function, I should just get back x. And it would be 3 times x plus 2 over 3 minus 2. And sure enough, if I cancel those, I would get x plus 2 minus 2, and that's just x. Okay, so that's how I can check if I've computed the right inverse, is when I plug it in to itself, or when I plug the inverse into the function, I should just get x. Okay. Now let's try these composition problems. Here we've got a function here. We want to compute f of g of h of x. Okay? So here's what I'm going to do. The first step is going to be, I'm going to leave f on the outside, and I'm going to take h of x, and I'm going to plug it in for x in the function g. Okay? So I take h of x, which is x squared, and I plug it in for x in g. And I would get 1 over x squared. Okay? So now this inside here is g of h of x. And now I want to take that whole thing and plug it in for x in the function f of x. So if I did that, I would get 3 times 1 over x squared minus 2. And if you want to simplify, you get 3 over x squared minus 2. Okay, so that is how we do that problem. We just take the functions and we plug them in for x in the other functions. Gotta remember, h is where we start. We always start on the inside and work our way out. So we plugged h into g, and then we took what we got and we plugged that into f. Alright, this last one here is just funny notation which they like to use to confuse you. Okay, when you see something like this, when you see this little h circle f, what it means is h composed with f, and what it really translates to is just h of f of negative 2. Okay? And the way we're going to solve it is in the same way as before. All we're going to do is we're going to take negative 2 and plug it into f. Okay? We plug, this is going to be equal to h of, and if we plug negative 2 into f, we would get 3 times negative 2 minus 2, which would be the same thing as doing h of, well, negative 6 minus 2 is negative 8. And now we're just going to take negative 8 and plug it into h, and we would get 64. Because h is x squared. I guess I could give an intermediate step here, just to be super clear. Would be negative 8 in parentheses squared. And we take negative 8 times negative 8, and that would give us 64. All right, so that is it. This is just a sampling of all sorts of different questions which we might see on an exam like this. Again, it's not comprehensive. It's just to give you an idea of the way that I ask questions on exams, because sometimes some students can find it to be a little bit different. In the home environment, I ask these kind of different questions. So I just want everybody to be aware of what's going on there. If you have any questions about how I solved any of these things, please come to office hours and I will explain in detail to your heart's desire. And I can give you more in-depth explanations and more graphs and pictures and all sorts of stuff like that. Okay, well, I guess that's the end of the video, so happy studying.